Alright, in the first video, we used the limit and secant line concept to find the slope of the tangent line to a curve at a point. And what we're going to do next in this video is to use the limit definition to find the derivative of a function. Alright, let's start. Recall that we defined the slope of the tangent line by using this limit concept. In fact, this part was referring to the slopes of secant lines, and we were letting delta x go to 0. When we pass the limit, we get the slope of the tangent line by using this formula. And now I'm going to use the same exact formula to define the derivative of a function f at point x. Okay, so I'm just replacing c by x, but this time I'm going to denote this limit, not the slope, but f prime of x, provided that the limit exists. Okay, so if this limit in fact exists for every point x, then f prime is going to be a function of x. So the derivative, if it's defined by this limit for all x, is going to be a brand new function, and that's going to be called the derivative of f. And the process of finding the derivative of a function is called the differentiation. Okay, and we say like a function is differentiable at x when its derivative exists at x. Okay, and we can say like f is differentiable on an open interval a and b. That means that f is differentiable at every point in the interval. And you will hear that whenever we talk about the derivative, and that's sort of like tied up to the instantaneous rate of change of one variable with respect to another. This is sort of like versus the average rate of change that we have seen in pre-calculus, but I'm going to talk about this specifically on examples. And here, let's talk about the notation. So obviously, we have this nice notation f prime of x, but we have some other notations that we're going to use along the way. So here is one of those, dy over dx. Okay, so another one is going to be y prime, or d over dx of in bracket f of x, and by this we're going to understand that we're talking about the derivative of the function f, and this one is the operator notation, what we call operator notation. So d sub x of y, again, these are all referring to the first derivative of the function. And now we're going to read dy over dx as the derivative of y with respect to x, or simply dy over dx. And using the limit notation, we can also write dy over dx as the limit as delta x approaching 0, delta y over delta x. So deltas turn out to be d's after you pass the limit, and these are all represented by f prime of x. And out of all of those notations, this notation, dy over dx notation, is particularly important because when we talk about the higher order derivatives, this is going to be helpful because let's say like if I ask you to find a 10th derivative of a function, you can't put like 10 primes on top of f. That's not feasible in terms of space use. But we're going to use this notation. We're going to tweak it a little bit. You will see how helpful this dy over dx notation. All right, let's finish this video by going through this example, which is about finding the derivative of the given function x cubed plus 2x by the limit process. So all we're going to do here is to use the limit definition here. Okay, f of x plus delta x minus f of x divided by delta x. You can also say that this is equal to dy over dx in the other notation. Okay, so all we're going to do is to write down the top explicitly. What is f of x plus delta x? I'm going to replace x by delta x in the description of f. So this would be x plus delta x cubed minus 2 times x plus delta x minus, let me use a bracket, minus f of x, which is x cubed plus 2x. And this is all divided by delta x. So again, if you pass the limit at this moment, and remember from chapter 2 by using the direct substitution, you're going to run into obviously 0 over 0 case. We don't want to do that. What we want to do is to simplify the top and see if there is any cancellations. We're essentially using algebra. All right, let's expand the top out. So this is x cubed plus 3x squared delta x plus 3x delta x squared. This is the cubic power, by the way. I'm using the expansion of that. Then delta x cubed plus, okay, minus x cubed minus 2x. And then this is all divided by delta x. All right, let's see the cancellations here. So we have x cubed canceling this x cubed, and we have 2x canceling out this 2x. All right, let's continue from here. So the top is going to be 3x squared delta x, 3x delta x squared, and delta x cubed to delta x. Okay, and this is all divided by delta x. And do you see the commonality between top and the bottom? Well, delta x apparently is a common factor at the top, and that's going to allow me to cancel out delta x's in the next step. Okay, delta x factored out, and this is all divided by delta x. And remember that delta x in the bottom was causing the 0 over 0 type indeterminate form, but after using algebra and rewriting the top, now we can cancel out or divide out delta x's, right? This is almost like the dividing out technique that we learned earlier, right? So we can divide them out, and this limit turns out to be the limit of 3x squared plus 3x delta x plus delta x quantity squared plus 2. Now I can pass the limit because delta x itself is approaching 0, so I can use the direct substitution. So essentially, these terms are going to tend to 0, and I'm going to be left with 3x squared plus 2, and which is in fact what we call f prime of x. So the derivative of the function x cubed plus 2x is 3x squared plus 2. All right, in this video, we achieved this learning objective, in fact, using the limit definition to find the derivative of a function, and we had an example for that. And in the next video, we're going to try to understand the relationship between differentiability and continuity. All right, I'll see you in the next video.